Hello, everybody. Thank you for joining today's webinar. It's the third and final webinar in our series focusing on supply chain hazard awareness. And today we look at shock and vibration. What are they and why should you care? So if you've missed the first two webinars and would like to view it, there's a link, or I will place a link to the on-demand in the chat box now. That's just for you to view at a later stage should you want to. Before we start, however, I wanted to go over a few things. So as you know, this is a Landsmont Corporation webinar. Landsmont falls under the umbrella of the Physical Properties Testers Group, or PPT for short. Some of the other companies under that same umbrella include McMesson, James Hill, and Telluris. If you're interested in learning more about any of our partner brands, you can visit the PPT page and see the content and on-demand webinars they have available. That being said, I wanted to introduce some people on today's call. Eric Jonassen is our presenter for today, and my name is Sharon Smorenberg. I'm one of the organizers. Then we have various support staff throughout the United States, Europe, and Asia. So please feel free to ask questions. We would like to keep it interactive, so you can use the question box throughout the webinar to type in any questions you may have. We will then address the questions at the end of the webinar. This webinar is going to be recorded. You will get a copy of the recording to the email that you registered with. If you want to review anything for additional clarity, or if you have a colleague who is interested in attending but wasn't able to make it, please feel free to pass the recording on to them. And with that, I will turn it over to Eric.
Okay, thank you, Sharon. I'm going to just turn on my camera real quick to introduce myself before I get going. So thank you, everyone, for taking the time to join us today and listen to me explain a little bit about shock and vibration, something that's kind of important to me. And this is the third webinar that I've delivered here over the last 6-7 weeks, talking about supply chain hazards. So now kind of going to get a little bit technical, talking about shock and vibration. A little bit about myself. I am Landsmont's Vice President of Technology. I've been with Landsmont my entire career after graduating from university with a packaging degree. But I do consider myself a shock and vibration measurement and testing kind of nerd or experienced engineer in that space. And so I'm going to share a little bit about subject matter of shock and vibration, which is hard to do, quite frankly, in only 30-40 minutes, just because of the technical complexity of it all. But I think this will be a nice overview and hopefully lead into some future webinars in our plans. So I'm going to go ahead and turn my camera off as I move forward, just so I can concentrate on the slides. And here we go. Thank you. So once again, this is the third in the webinars where we're talking about things like supply chain hazards. And we talk about supply chain hazards, we're talking about all these things, these dynamics, kind of dynamic hazards that exist in the supply chain as we're moving products from the point of manufacture to the end user or the consumer. And we are talking about this, you know, kind of my experience with this is someone that's involved in the measurement of it, and the measurement and characterization of those types of dynamics using our Sabre technologies, our field data recorders, portable self-powered field data recorders. So I'm coming from this discussion from that perspective as someone that measures and characterizes and tries to explain those types of dynamics and make sense of those as we move forward. And so where do those kind of hazards come from? These are just quick videos that show examples of all those types of the different, transportation and handling dynamics that take place that expose things, packaged products, to shock and vibration. really those two types of dynamics, which we'll talk about moving forward. And so why do we care about this? Why do we care about these two dynamics that we call shock and vibration? And it's basically because those types of dynamics, shock and vibration, can excite products and packaging. And basically that means if we put some type of dynamic input, shock and vibration input, into a product or into a package that is containing a product, it's going to generate a response. And so these are actually videos of different things that are shaking and resonating. This is a large product that you're seeing on the right-hand side of this video that's playing, with a lot of complex hardware underneath the cover. And you're watching it undergoing a vibration test on a vertical vibration test system, and you're seeing the types of responses that really occur when you input vibration and see those types of responses. So we care about it because, again, packages and products can get excited by those types of dynamics. And so we are concerned, obviously, what level of excitement they experience. So when we talk about shock and vibration from a basic dynamics perspective, we're really talking about changes over time, or changes in the time domain, what we call in the time domain. And those are changes in what would be position. So think of how far is, from a distance perspective, changes in position, changes in velocity, speed, and changes in acceleration. So we're really focusing on these three areas and kind of understanding how those changes take place. When we talk about changes of position, it's pretty straightforward, right? Position is something that's defined in terms of distance, miles, kilometers, inches, feet, meters. So we're talking about changes of position in terms of distance. And then when we talk about velocity, velocity is actually defined as the rate of change of position. So as we move from point A to point B, we move at some speed, right? And that's the rate of change of position. And that's typically displayed in terms, or defined in terms of miles per hour, kilometers per hour, feet per second, meters per second. But those are the types of measurements that we define when we're talking about velocity. So it's the rate of change of position. And then acceleration is the rate of change of velocity. And we define that in terms of its measurement characteristics in terms of inches per second squared, meters per second squared, or in G's, which is what we'll talk about moving forward. So what's important to understand, just the last kind of note here on the basic dynamic side of things, is there's these displacement, velocity, and acceleration are all related to one another mathematically. And so what I'm showing here on the left-hand side is if you measure acceleration over time and you integrate that mathematically, you get velocity. And if you integrate velocity, you get displacement. And so I'm just trying to make, again, the point here that those three things are mathematically related to one another. So we can learn a lot from just measuring things like acceleration over time. We can calculate by integration the velocity, and we can also calculate displacement, all from that type of measurement. So what's the difference between shock and vibration? The reality is there is no solid definition of shock and vibration. It's more about the characteristics of how we define shock and vibration. Things are shock-like, that might happen. Dynamic has shock characteristics, and other measurements or dynamics that you see in supply chain have more vibration-like characteristics. And so there, again, we measure them the exact same way. We measure them with accelerometers, with sensors that measure changes of acceleration over time. So there's really no difference in the source. It's more of then when you look at those measurements, how you characterize what you see. And then put it into kind of a deflect it into one bucket that says that's shock-like versus pushing it in the other direction that says, that looks more vibration-like. So I'll explain kind of how we come up with those, decisions on how we characterize things. From a shock perspective, just in defining, kind of the shock characteristics, we say it's non-periodic excitement of a mechanical system characterized by suddenness and severity. That's the kind of key words there. Shock is sudden and it's severe. That means it's quick. Think of it slapping my hands together. It's quick and it's severe in its overall amplitude. The events are transient and they're not continuous dynamic events like vibration. Just like, again, if I bump my hand one time, I take a shot, but that doesn't continue. It's a transient event. It occurs quickly and then it's over. As a result, shock typically causes significant relevant displacements in the system, or say in the product or in the packaged product system, that results in immediate damage or failure. And you can almost think of that as catastrophic type of failure, structural failures. And we describe shock by a shock pulse, which looks something like I have on the screen there, which is really a change of acceleration over time. So the y-axis of that type of a pulse is an acceleration, and the x-axis is time. And that's how we describe shock. What they look like, these types of impacts. Things that get dropped, things that get bumped, rail cars that come together when they're being built into one long train. Those are all things that result in sudden and severe types of acceleration dynamics. Shock is characterized by a rise and decay of acceleration in a short period of time, and we typically display those graphically as curves, acceleration curves, acceleration versus time curves, or acceleration versus time waveforms, which is being shown on the screen right now. Acceleration can be a change in speed, or it can be a change in direction, or both. So think of something speeding up or slowing down, or think of something going down the road and turning to the left or turning to the right. When that happens, if it happens suddenly, you experience acceleration in one direction or the other. Acceleration can be positive or negative. Again, think of a box or a crate that's sitting on the ground, and somebody walks up to it, or a forklift comes up to a crate and it hits it on the left-hand side. That's acceleration in one direction, which we might call a positive direction. But if the forklift enters on the other side of the crate and hits it on that side of the crate, it's experiencing acceleration in the opposite direction, or in the negative direction. It's still called acceleration, but it's just directional, right? It's got direction associated with it, positive or negative, which really, again, means which side is the acceleration being experienced in, say, a product or a package during a shock event. Shock pulses are described by their waveform. Again, there's an acceleration versus time waveform. Okay, so it's not just a number. When an event happens or a shock event happens, we don't just say it was a 20G event or it was a 30G event as a way of describing the severity of that event. Many people do, but you can describe it that way, but it's, again, a lot of this is from experience and opinion, but that says that's a very risky thing to just describe a type of an impact or a shock event solely based upon its acceleration level. It's really more important to understand the overall waveform, the total event over time. And so when we describe a shock pulse, yes, we do describe it in terms of its amplitude, which is on the y-axis or amplitude. We do define it in terms of G's, but that shock event also has characteristic called duration associated with it. which is time. How long did that event take place? And when we talk about shock events, the duration of these events, whether it's shock that occurs from dropping a product right onto the ground, onto concrete, even onto carpet, or dropping a product in a package on the floor, the duration of those events is short. It's less than a second. Realistically, if it's even in a cushion package, it's in the tens to maybe 100 milliseconds in duration. Very short. Tenths, that's a tenth of a second. So it's a whole different world here where things happen in very short periods of time. But that is very important. It's very critical to understand that the duration of these events when we're trying to understand the severity of these events. And from that, understanding the duration, we also can characterize or describe shock pulses in terms of their frequency content, which is also very important to understand, because that tells us how if I expose a product or a packaged product to a certain type of shock pulse, understanding the frequency content of that shock pulse helps us predict how damaging that shock pulse might actually be to that product. And then one last real kind of key critical piece that we get from analyzing a shock pulse or characterizing a shock pulse is something that we call velocity change, or the delta V associated with that. And when you look at this shock pulse, what I did there is I shaded in the area underneath that yellow waveform. So I shaded that area in, and it's the area below that yellow acceleration pulse and above the zero line. So what that area, when I calculate or integrate, that's really the integration of that shock pulse, that shaded area equals velocity change. That's how we calculate that value. And so once we have that value, we couple that with the amplitude of the event, the peak amplitude of that event, as well as the duration of that event. With that velocity change, we can then describe that shock pulse. Instead of just saying it was a 30G event, we say it was a 30G event over 26 milliseconds in duration, and it had a velocity change of, in this case, 200 inches per second. Having all of that information really gives us the ability to much more clearly and confidently describe the severity of that event. And quite frankly, when you think of velocity change, because it's speed related, we really think of that as being something that's proportional to the overall energy of that shock event. And that's because kinetic energy is directly proportional to velocity. So this is a really more powerful way of describing the overall severity of event when you look at the event in the complete time domain. And then lastly, I mentioned about frequency, right? Shock in the frequency side of things. How do you get frequency from a shock pulse? Well, this is another shock pulse waveform that I'm showing on the screen here. In this case, about a 75 to 80 G shock pulse. But what we know from that shock pulse is the duration, right? So we know the duration, that's a measurable thing. And in this case, I have a 10 millisecond shock pulse. Well, if I think about what we call that waveform, when we look at those, we call those half sine shock pulses. They have a half sine characteristic to it. What does half sine mean? Well, it really means half of a sine wave, right? So what I did just now is I overlaid basically the equivalent of a full sine wave instead of just the half sine wave from the blue trace. If I take that same shape and extend it out, it goes from being a half sine to a full sine wave. And as long as we know that what that wavelength is, or it's the period of that wavelength, we can calculate the frequency of that wave, right? So just a simple formula up on the right hand side there that says the natural frequency of that pulse equals 1 divided by 2 times the duration, which it was a 10 millisecond shock pulse. 2 times that is 20 milliseconds. Or another way of saying that same thing is it's, the frequency is 1 divided by the period of that sine wave. In that case, it says that shock pulse has a natural frequency associated with it of 50 hertz. And so that's really important to understand, and I'll come back to that towards the end of this presentation, but that's really important to understand because not only, again, can we describe the severity of that shock pulse by its amplitude, its duration, and its delta V, but knowing that frequency, what we can also say is if I have a product and that product has a vibration natural frequency or a resonant frequency of 50 hertz, I'm likely going to have problems on my hand because if I expose that shock pulse with that natural frequency to a product that has that natural frequency or a package that has that natural frequency, it's like a worst case scenario. It's going to be something that has a huge response as a result of that. So it's really important, again, and powerful to understand amplitude, duration, velocity change, and the frequency characteristic of shock pulses as they occur in the real world. Okay, moving forward now to vibration. So talked about shock, let's talk about vibration. What's the difference between vibration as it relates to or compares to shock? Vibration is different in the fact that it's oscillatory motion about a reference position. So there's an example of a oscillation. It's a fixed frequency sinusoidal tone that's got a kind of modulation associated with it, kind of a wah-wah factor. If you think of what that would look or sound like if you were to play that back, it's a frequency, fixed frequency sine wave, but a modulated where the amplitude goes up and down, up and down, up and down. But it's oscillatory motion about a reference. So it's not shock-like, right? The shock before was like boom. It had a half sine to it, but it's kind of flat before it, goes up to some extreme, typically, comparatively, extreme acceleration level, and comes back down to that zero reference line and dampens or attenuates out. Vibration is oscillatory, and it's steady state. It continues for a long time. You're seeing my waveform down below the screen here. It's continuous, right? It goes across the screen from left to right, and quite frankly, you could go on to the next slide, to the next slide, and to the next slide because it's continuous. Vibration is continuous. So when something is moving in the supply chain, it's going to experience vibration. Shock may or may not occur, right? It's transient, and it may happen or may not. It's typically, shock is associated with some type of handling in the supply chain. Will somebody handle this? Will they mishandle it? There's probabilities associated with that, whether the occurrence takes place or not. With vibration, the second the truck, the train, the airplane starts to roll, starts to fly, starts to go down the road, it's going to experience vibration. There's no questions about it. You're going to have to deal with it. And where shock tends to cause catastrophic failures, or to think of structural failures, or something breaking immediately as it's exposed to that type of dynamic, vibration causes things like cumulative fatigue related problems or issues, wear issues, abrasion, loosening of parts. Think of fasteners, screws backing out in a product. Over time, they back out, and when after they back out, something becomes dislodged or free to move within that product. We have abrasion when things are shaking in respect to one another, maybe even two packages side by side, two bottles side by side. As they're shaking, it's almost like an abrasion test, right? Especially if that shaking in some way or the other becomes out of phase. Those bottles or packages rub against each other, and they cause abrasion, maybe label scuffing. It's cosmetic, which can be a problem, but it can also be structural when things are shaken with respect to one another. things like aluminum cans when they're really lightweighted. If it exposes or experiences too much of that fatigue, quite frankly, it can wear right through the can and start causing leakers. I'm familiar with many real world examples of that type of a failure. So that's not a huge catastrophic structural, that didn't happen from an impact, that happened from shaking that's been taking place over a long period of time, like a cross country or a cross continental shipment. And we typically describe vibration by its amplitude, same thing. Amplitude in terms of acceleration, its frequency, and the type of vibration, which is sinusoidal and random. And I'll talk about that moving forward. What you're looking at the bottom of the screen again is an example of a sine wave, modulated as far as the amplitude going up and down, but that's a sinusoidal signal. The frequency doesn't change. It's sine in its nature. Last little bit of kind of math here. When I'm not going to get into a lot of detail on this, but products and packages and packaging materials have things, characteristics associated with it, which we call its natural frequency or its resonant frequency. Basically, that means when it shakes, there is a specific frequency where it really gets excited, where it likes to shake more than the input that's being put into it. And so we can determine that in a laboratory with an engineering test that we call a sinusoidal resonant search frequency sweep, where we use a vibration table in a lab and we shake it through a series of different frequencies. We sweep through a series of frequencies, which I'm kind of showing on this plot just think from left to right. We start at a low frequency, move the table up and down at a controlled amplitude or acceleration intensity, and then we speed it up. We shake a little bit faster, 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 until we get out to an endpoint on the right-hand side. And what we do is we measure the response of how our product or packaging that's mounted to that table responds to that input, table input. And wherever the peak of that is, where the product, the component, or the packaging has the maximum response, we call it the natural frequency, F sub n, or its resonant frequency. And that's really, again, critical to understand, because basically that frequency and the amplitude of it, the Y amplitude, how high that response is, relates to the kind of the potential for damage in the real world from vibration. So it's important to understand that from an engineering perspective. And this is kind of what it looks like, all right? Just a segment of a frequency sweep here. So what I've got on the screen here, what you're looking at, are just some what we call spring mass models. If you can see my mouse here, these all are masses, round masses, different masses, heavy, middle, kind of mid-weight, and a lightweight disc that's mounted to a spring. Those springs are the exact same between these three models. The only thing we're varying here is the weight. And if I put them on a vibration table and I sweep through these frequencies, what you're going to notice is, as I sweep, is that they all shake at kind of get excited at different frequencies. Let me just play that real quick. The table is sweeping. Hopefully you can maybe hear it. There's the natural frequency of that spring mass system. Table keeps sweeping higher. There goes the second resonant frequency. And now even at a higher frequency, you see the third one. And so we're able to measure those things, right? So that was just kind of a visual with the video, but we're actually able to measure those in a laboratory environment with instrumentation or sensors. And so what you see there are traces associated. These are sine sweeps. Think of it as a sensor being on mounted to that mass. This sensor would have been mounted to this mass, and this sensor, or the sensor that this data came from, would have been mounted on this mass. And so what you see there are three discretely different resonant frequencies. The big heavy mass has a lower natural frequency than the mid-weight mass, and the lightest mass has the highest natural frequency. So we can actually, again, define those, and it's really, measure those and define those resonant frequencies. And so those are simple spring mass systems that we use for demonstration, but what you can really think of is products can have those same types of real spring mass systems, a number of different types of spring mass systems. You can think of, let's say, a computer system or a medical instrument that has a display that's on an arm with a computer in the base and a power supply and the wheels and casters. All those different pieces and parts and components may have natural frequencies just like these spring mass systems. And so it's important to understand those so that we know what we have to protect against in the supply chain with packaging. So vibration, this is what a sinusoidal input looks like. Remember that sine wave. So this is what would be considered a sine wave. And this is more of kind of what we would put those products through one of those vibration resonant searches. Obviously that sine wave changes. We sweep through a number of these different frequencies. But this is, again, an example of what a sine wave looks like, sitting at a fixed frequency and dwelling there. But if we move that, forward, that changes over time. But in the real world, this is what vibration looks like. We call it random vibration. And it doesn't look right. It doesn't look like that nice, pretty sine wave. It looks messy. It looks noisy. And that's because in the real world, it is that way. Why is it that way? Well, when trucks go down the road, you have a lot of different things taking place. When it goes down the rails, the same thing, you can hear it. So there's a lot of different things going on in the real world that contribute to the vibration that's experienced. It's not just a sinusoidal tone out there when you're going down the road or in an aircraft or going down the rails in a train. Lots of things contribute to that noise that we would measure and try to reproduce in the laboratory. And so what I'm showing here on the screen are just some examples of some random vibration test profiles. We call these PSD profiles. PSD stands for power spectral density. I'm not going to go into a lot of detail there, but what you see, there are different ones here. There's a steel spring truck profile, meaning the suspension of a truck trailer, an air ride suspension, an aircraft PSD, a rail car or a box car PSD. Each of those transport modes basically has a signature, a vibration signature associated with it, which basically means when it's in that environment, it responds a certain way. It has a certain look and feel to it from a vibration perspective. And so you can think of these as being kind of almost like noise signatures or representations of those transport modes. And you say, well, where does that come from? So here's, a truck trailer. Look at a truck trailer, for instance, where you might ship your products, packaged products inside that truck. You get contribution from vibration comes from a number of different sources here. It comes from, you're seeing airbags or air suspension there. This is different types of suspensions under trucks. It could be steel springs, which is a little bit more, becoming maybe less common in certain geographic areas where air suspensions are becoming more common. And it's because it's a better quality of ride, typically a better quality of ride. But that has a very specific frequency response characteristic to it, as does things like tires and wheels. It's different. These wheels and tires put in vibration into the packaged products that are inside of a truck trailer. That's different than what the suspension is inputting. And the rigid body structural members of a truck trailer, that's different from the tires, and it's different from the suspension. All of that stuff is shaking and generating energy in a specific way, with a specific frequency associated with it. And so that makes for that noisy looking waveform that I showed earlier. And so there's just kind of a way of saying kind of how we can take that noise. In this example, here's a waveform up at the top of the screen. That's a randomish looking noisy signal. But we have ways with technology of saying, okay, if I look at that waveform, that noise, I can basically put it through certain types of filters. It's what would be called a type of an FFT analysis. But just say it's kind of putting it through filters to pull out certain types of content from that messy waveform. So if I say, I look at this waveform up at the top, this light blue one, I can actually say, well, here's the 2 hertz kind of signal I see in all that noise. And if I could have dragged this up on top of there, you'd see, 2 hertz is kind of showing this characteristic in that waveform. Here's the 4 hertz energy that we see in this waveform. Here's the 10 hertz energy. Here's the 20 hertz. Here's the 60 hertz. And here's the 100 hertz energy that all are embedded within this one kind of noisy signal. And why is that important? Or how do we use that? Well, it's because when we look at these PSDs, these power spectral density plots, the way we describe these and use these in the laboratory environment, what we do is we take that information that we get from the real world, or from that noisy real world vibration signal, and we pull out that 2 hertz content and we plot it on one of these PSDs. This is just a simple example, but we say, all right, on average, this is what the 2 hertz energy looks like from that field data. So let's plot that on our PSD. Let's do the same thing with our 4 hertz energy. Let's do the same thing with our 10 hertz energy. Let's do the same thing with the 20, the 60, the 100. We do that, across that whole spectrum, and that's basically how we generate these signatures, or these PSDs, is by measuring all this noise and pulling the specific frequency content out of that to build these PSDs. And what those PSDs, again, let's say, where does that breakpoint, or that for instance, this 2 hertz noise or energy come from? Well, that's a characteristic of this truck suspension, of an air ride suspension. What's that bump, associated with? Well, that's from, think of tires and wheels rotating as they're going down the road, spinning at a certain frequency, right? They rotate, they spin at a certain frequency, and that provides that kind of content that we see in a PSD. And then what about these next ones, are at the higher frequencies, this peak? That's intensity or vibration energy associated with the rigid body members, the frame of the trailers, the sidewalls of the trailers, the floor of the trailers, the rigid body structures, and how they respond. All of that, as a truck is going down the road, is occurring simultaneously. So we build this kind of noise profile, or this PSD profile, to simulate that all in the laboratory. Okay, so back to shock real quick. Remember, I showed this waveform, right? This waveform has a natural frequency, we calculated that natural frequency of that 10 millisecond shock pulse to have a natural frequency of 50 hertz. So it's a 77G 50 hertz shock pulse. Well, remember when I did this sine sweep, I was able to measure that lightest mass on that spring had a natural frequency of 46 hertz. So that's shaking at roughly 46 hertz right now, and you see what's happening with that spring. It's really dancing. It's really going crazy. It got super excited and really likes to respond with an energy greater than what the test input is, the table input. So the point there is, if it's got a natural frequency of 46 and that shock pulse, let's say that widget or that spring, I didn't do this, but if I was able to expose that spring to that 77G 50 hertz shock pulse, what do you think would happen? What would happen is that spring would probably, potentially get so excited by just that one huge input that, quite frankly, I probably could separate that mass, the weld. I could probably break the weld because it would respond to that. they both have the exact kind of frequency content, right? The shock pulse, whereas the same where that natural frequency of that spring mass system is. So if I give it a big shock pulse, not just the number of 77 Gs, but also what I would say tuned to that same frequency or about that same frequency, that's asking for trouble. That's asking for almost like a catastrophic response where it will very likely, again, could either break that spring or break the weld between the spring and the mass itself. So it's kind of really important, again, trying to point out that to understand all that content and how they relate to one another. Quite frankly, even shock and vibration. They're, again, measured from the same thing, acceleration versus time waveforms. And it's important to think of them together because they impact one another. And so last slide, role of packaging, which is really kind of setting up for future webinars and discussions that I'd like to host moving forward, probably after the new year. But how do we use packaging? We use packaging to mitigate that energy, right? We use it to mitigate it, to filter it. Just these are different words kind of meaning the same thing. Attenuate it and dampen it. And not only that, it's not just throw packaging materials at products or within transport packaging, but there's actually an engineering process that you can go through so that you can engineer or design packaging specifically to mitigate or attenuate those energies from ever making it through the packaging to the product itself. I always think of it as almost like you think of it as the foam earplugs that you would put in your ears to block out sound. That's exactly what that's doing. Sound is vibration, and when you put those earplugs in your ears, you're actually filtering the sound from getting to your eardrums. It's the same thing with noise cancellation headphones or earbuds. It's acting like packaging, right? Those foam earbuds. Think of a bigger piece of foam inside of a packaging supporting the computer or the other piece of electronics that's inside that packaging or the medical equipment. It's filtering that energy, that same type of energy from ever making it to the product. And that's kind of how it works. That's a role of packaging when used in the engineering sense or perspective. Okay, with that, thank you. Appreciate the time and attention. Hopefully leave some time for a few questions. I was really trying hard to get done in a time where I could allow that to happen, and I think I may have succeeded. So Sharon, I'm gonna go ahead and open it up. And I'm not looking at the control panel, so if there are questions, maybe you can help me out. Thank you, everyone.
Thanks so much, Eric. That was great. I have got a few questions, but just an invitation to everybody else. If you have any questions, now would be the time to put them into the question box. So, Eric, I'll start by reading the first question, and it is, my biggest question when reviewing the vibration section of the ISTA manual is how you're supposed to determine the specific frequency of whatever product you're testing.
And you see my email here, so I don't want to ever make it sound like I'm trying to dodge questions, but I'm trying, in the interest of time, I'd say I don't quite understand that question. So just I would say is the ISTA vibration, any vibration testing incorporated into an ISTA test standard is really a simulation of a transport environment. Again, it could be a truck profile, a rail profile, an air profile, some type of delivery vehicle profile. So it's not, when we look at those profiles extend over a frequency range. It's not a specific frequency. They typically extend over a range of something like 1 to 200 hertz. So it's covering all that frequency. Back to how I described the PSD profiles is almost like noise profiles, right? It's noisy, it's messy. There's all kinds of stuff going on. So it's not a discrete frequency. The discrete frequencies that I talked about, talking about resonance, that's something that you do more of an engineering test that's separate from doing, let's say, an ISTA or an ASTM 4169 type of a random simulation. They're two different tests completely. I don't know if that helps answer that question. And if not, again, either expand on it or type more, or feel free to reach out to me directly.
Thanks, Eric. I can also share with you their contact details, but
Okay.
I think there is another question. So the next question is regarding the different profiles. Would you recommend
Yes.
enveloping all of them and run one random vibration? I would imagine the intensity would be extreme, but it would be considered a margin test and would weed out any failures in the long run.
Yeah, I think that's, yeah, I mean, it all kind of depends on the intent of the test, which is just you described, Sharon, or the individual described. You know, you could justify that or rationalize that. You know, you have to understand what it is and what it isn't at that point, right? And then you have to make a decision based on, I would think, on risk and whether, you know, you want to, what's the risk benefit, cost benefit of using a profile like that, you know, and so it kind of, how you answer that question kind of maybe depends on what kind of product you have. Is it a medical product versus a food product? You know, for instance, if it's a biological product versus cereal food product, you might be able to accept some level of damage or failure if it's the cereal product, because it's really not going to damage it might not look brand new when you open the package, but it's going to taste the same. It's not affecting the food quality. But if I over test, let's say, a protein, a biological product, by using some combination, you know, look at, again, upper envelope or enveloped PSD profile that covers all these different profiles. Well, that never happened like that in the real world. And if I use that in the laboratory and I fail, my product fails, my packaged product, as a result of using that, that's risky, because now you've caused a failure, and that failure needs to be investigated. And that failure could have been caused for, you know, not valid reasons, or it might be hard to explain the reason for that failure after the fact. So I think there's a place for that, but I think it's a matter of, you know, kind of a risk assessment at that point of what you're trying to accomplish, you know, and understanding the pluses and minuses to that approach. I don't know if that makes sense or not.
Thanks, Eric. I'm going to go on to the next question. I often hear that we don't need to run a vibration test on a product, that we complete production on a year prior and test it before. Does that sound valid? I think production processes should be validated each run, but I always hear otherwise.
I haven't heard, I guess I'm not familiar with that specific scenario. I guess just trying to understand what the question or the point there was is, yeah, I mean, to me, it seems like an awful low risk thing to, I would not assume anything remains unchanged, as simple as it would be to run, you know, a vibration test one way or the other, whether that's product vibration test or even the random simulation, transport simulation. I would definitely, you know, myself lean on more caution and rerun the test. I think if I understand that correctly, it would seem like the safer way to move forward, just to prove, you know, to put yourself in what a word that I like other people use when they talk about testing is put yourself in a defendable position. You can defend what you're doing based upon the data that you have that you stand behind, versus saying, I don't think we need to worry about it because nothing changed from last year. Well, you know, I would rather prove that than assume that. So I would say err on the side of caution and rerun the test. It's not like, to me, they're relatively low, I think anyway, but investment in time and resources to rerun these types of tests.
Thanks, Eric.
Mhm.
Another question, is it possible to separately find the dampening effect brought by pallets and packages?
Yes. Yep. And quite frankly, yes. So absolutely. And stay tuned, I guess is what I would say. I mean, I'm more than happy to talk about that one-on-one, via email. But that is my intent also to show some literal examples of that in upcoming webinars that we have not, published our plan or schedule yet, but we will be shortly after the first of the year. And that starts getting fun to me, is to show how that can be done. And I have real world examples of that myself that I'm willing to share.
Awesome. Can one find the resonant frequencies by random vibration, or must it
Yeah,
be?
you can. Yep, you can for sure. The frequencies you can run whereas running a sine sweep might take some period of time to run from a low frequency up to the higher end frequency and then back down. You can run a random vibration test with that same instrumentation on the table and on the product or the critical component, and you can expose it to maybe 10 seconds, quite frankly, or 20 seconds or 30 seconds of random vibration, and see that, identify that same natural frequency. What you don't get with that approach necessarily, you would not get the same Q level, meaning the maximum response. You'll get probably a higher response always during the sine tests as compared to what you would get in the random test. The frequency would be the same that you identify, but the amplification would be more in the sine test, because in that test you allow more time for the item to respond, because the sweep goes slow. It's slow and it kind of doesn't ever stop, but it's dwelling longer at each of the frequencies in the sweep than it would in the random test. In the random test, the amplification is continuously changing at any frequency that it's shaking at. So you'll identify the frequency, but the peaks may be a little bit different.
Okay, we've got a follow-up question from the person who asked the first question, which was related to the ISTA guides.
Mm-hmm.
And he said, I asked the first question and I think I understand. My follow-up question would be, what is the benefit of doing a sweep program version? This version, I don't know if you wanted to say versus, but it's written here, version, the spectrum programs that seem to plateau at different frequencies and vice versa.
Yeah, they're completely separate tests for why you would perform one versus the other. So the sine sweep is really more of an engineering test. It's an engineering test to define, to kind of, let's just say that back to this is a whole future potential webinar, which would be fun. But the sine sweep is really meant to test products or packaging to find out specifically at which frequency or frequencies they like to shake or get excited. So where they respond with a greater response than the input that was being put into them. And once you learn that, that is what allows you, if you are willing and able to take the effort to, or commit the resources to engineer a packaging solution, it's what allows you to engineer the packaging to protect against or mitigate the amount of energy that can get through the packaging at those frequencies. And then what you do is you use the random vibration profiles as kind of the validation test to prove, okay, now that I've designed my packaging and I've kind of proven out that I'm filtering or attenuating vibration at certain frequencies, send it through a truck shipment simulation and prove that it not only kind of works from the design perspective, but it will actually work in a full transport simulation. So they're two different, completely different tests. One's engineering, one's really transport simulation.
Okay, I think the last one that we have time for is, where is the best place to start when you're testing a new class of materials in shock applications?
Well, again, that's a probably need more clarification on the question and probably another complete webinar just on that. But one thing, that is are published by people that's, for instance, if you have a sensitive product and you're wanting to protect against shock by using either cushioning materials, foam materials. Some people, depending on how big the structures are, might use coiled spring cushioning or dampening materials underneath that. There are typically shock and vibration, what are called cushion curves. Especially for sure there are shock cushion curves, and those published cushion curves allow you to or help you focus, on the right type of material and the right amount, right thickness, and the right area. For instance, again, not just the thickness of the cushioning, but how much bearing area or static loading of that material that you need to use to mitigate shock from entering in to that package. And so those cushion curves are a good place to start. And there are, not only are there shock cushion curves, but there are vibration cushion curves that work similarly, different but similarly, in as far as allowing you to pick materials that will attenuate vibration energy at specific frequencies from getting into that product. And used together, those materials can really help you dial in, instead of just, again, arbitrarily using packaging materials, films, foams. It says use this foam, this 2-inch, this 2-inch foam, and use these 6 blocks or 3 runners underneath that pallet deck, and that will help you attenuate all that energy from ever getting through the pallet up into your product that's inside that pallet.
Thank you very much, Eric.
Mm-hmm.
I think that's all we have time for, but if anybody has any further follow-up questions that you'd like to discuss with Eric, or maybe provide a bit of more background on the questions that you asked in order to clarify for him to be able to give you a more comprehensive answer, please contact him. His email is in the chat box right now, and you can see it on screen. It is eric_jonassen@landsmont.com. But again, thank you so much for joining us today. We look forward to hosting you on one of our future webinars, which I'm sure Eric has got many ideas on, but also if you have particular webinars that you are interested in seeing us host, please let us know about those as well. Thank you, Eric, and thank you for everybody. I'm going to end the webinar now. Thank you. Have a good day.
Thank you, everybody. Thank you, Sharon.
Thank you.